Hello, everyone. A very warm welcome to the Net Zero Energy Building Knowledge Series. This is a platform for industry to share their expertise, knowledge, products, policies, technologies, and even ideas to fuel the discussions on energy efficiency and grow engagements for net zero buildings in India. I am Deepa. I am a senior project manager at Environmental Design Solutions, and I shall be the session moderator today. The webinar series is executed under the MATRI program supported by USAID. MATRI is an acronym for Market Integration and Transformation for Energy Efficiency. MATRI supports three main program areas, which are energy efficiency in buildings, sustainable cooling, and training and consumer engagement. The program works in partnership with several organizations to implement various initiatives. The market transformation approach includes creating business opportunities for the private sector, scaling up of potential initiatives, enabling policies, as well as providing training for net zero energy buildings. METRI is supporting the efforts moving towards a super efficient and net zero energy target for buildings in India. The NZEB portal is a one-stop site for information on NZEBs, and you may explore this further on our website www.nzeb.in. So in our webinar today, we are going to discuss about cooling. This is essential and also largely energy intensive in the way it's approached for achieving thermal comfort, especially in the hot, humid tropical climate zones. Now, there is far more flexibility and opportunity to harness natural as well as mixed mode ventilation in residential buildings as compared to commercial buildings. And that's what our expert speaker, Dr. Yash Kumar Shukla, is going to talk about today. Dr. Yash Kumar Shukla is Technical Director of Energy Systems at the Center for Advanced Research in Building Science and Energy, that's CARBSE. He has more than 15 years of international experience in building energy efficiency research and serves as a lead on several energy efficiency research projects at CARBSE. His current research includes calibration of simulation models, performance characterization of envelope and HVAC systems, net zero energy buildings, and development of next generation control algorithms. He has extensive experience in the building management systems, building energy analysis, HVAC system operation, component characterization facilities, development of test chambers, building simulation modeling, and energy efficiency control algorithms. I welcome you, Dr. Yash Kumar Shukla. And before I hand it over to you, we have a little poll here for all the attendees. Just before we get started, to get an idea of how aware are all of you about low energy cooling ventilation strategies. So the poll is on your screen. Select the option that is best speaks to you. And this gives Dr. Shukla a context as to before starting the presentation. So send in your responses. We're already getting responses. We'll kind of wait for a minute. 30 seconds are up. There is an interesting mix of response coming in from the audience. We'll wait for 10 more seconds until a minute is up, and then we'll share the screen. Right. A minute is up and very interesting responses. Let me share the results with you. Yash, can you see the results as well?
Yes. Thank you, Deepa. Thank you for the kind introduction. And it's very interesting to see. This is exactly what I was expecting, is that many people are aware of the low energy cooling and ventilation strategies, but they do not know how to apply that knowledge. And it's also good that we have almost one third of the people who actually know how to design and apply these strategies in the building. So it's a very good mix. We have a very knowledgeable audience. We also have apparently few experts who are also knowledgeable in using these strategies. So I look forward to more interactive session at the end of the presentation.
Yes.
So
So I will make you the presenter now, and
okay,
over to you.
right, I'll share my screen. Okay.
Yes.
Okay. So I'm going to talk about low energy cooling and ventilation strategies specifically for tropical residences in the context of tropical residences. Why, before I start the presentation, I want to acknowledge that most of the slides and the knowledge is coming from a research project, low energy cooling and ventilation for Indian residences, known as LECAVIR. It's an EPSRC funded project and it's a collaborative project between Loughborough University, UK and CEPT University, India. We have several project partners: IEEE, SIM, SE Controls, ASHRAE Western India chapter, and ISHRAE, who has provided their knowledge in developing the strategy. So thank you to our project partners as well as the university that we are working closely with. So let me start with a little bit of background and context of this presentation. So this is a slide where you can see that buildings are already consuming significant 35% of energy, electrical energy, and annual increase is expected to be more than 8%. Further, the cooling energy in hot and dry climate is more than 60% of what the total energy of the building is. So it's definitely a very important domain. And with the rising per capita income, we are further expecting to increase the HVAC, we further expect to have a more penetration of HVAC systems in buildings and thus increase CO2 emissions more than 800%. So it's why this is a very, very pertinent time to look at low energy cooling and ventilation strategies. And on the right side is what I have is a concept developed by one of my students, Saranya, where in the presentation she was discussing what different strategies can be used in buildings. And I have taken that slide and modified slightly. But you can see that natural ventilation is very effective from the energy point of view, but often when the outside climate is extreme, it does not provide comfort. It fails to provide comfort to the occupants. When we use the standard mechanical cooling systems, we get good, comfortable environment in the space, but it takes tremendous amount of energy, as you can see about what I have talked about earlier. When we use low energy cooling systems individually, then the energy consumption is less of a building, but comfort is a mix. So there are periods of the year when you can get good comfort, but then there are periods of the year when it cannot provide a comfortable environment. So from the residential point of view, what would be a good combination is to not go away with a standard mechanical cooling system as the normal trend is, but to try to mix these strategies and what we often call as a mixed mode building systems, which we see should be the way future in tropical residences, where you combine the natural ventilation with the low energy cooling systems. And then you need to operate that building smartly with control systems and algorithms. So you determine when you switch between the natural ventilation as well as the low energy cooling systems. And then you club it with a comfort model, which is not relying on a constant temperature, but you actually use an adaptive comfort model where the occupants who've been living in tropical climates have been studied and known to be more adaptive than the certain other occupants who have not been living in tropical climates. So you can use a more evolved model of adaptive comfort model to further improve and increase the energy efficiency of building. So when you combine all these four different strategies, natural ventilation design, enhancing your natural ventilation strategies, you use a low energy cooling systems, and combine with the controls and an adaptive comfort model, you actually you can achieve energy and comfort both aims in your building. So mixed mode building is definitely a path forward in India as well as in tropical climates. So let me talk a little bit about the adaptive thermal comfort model. So some of you may be aware of this, but if you are not, then adaptive comfort model has been studied extensively in last 20-25 years. And it has been shown again and again that people who have been living in natural ventilation building or who have been exposed in certain environment do not need a constant temperature, but their neutral temperature, a temperature where they feel a neutral comfort, or their thermal sensation is zero, is changes based on the prevalent outdoor condition. So here are the two lines, one line which is showing an ASHRAE adaptive comfort model, which is a thick black line, which shows that as the 30-day running mean, that means the weather of the outdoor 30-day changes over the year, your comfort expectation, your neutral temperature also increases from roughly 21 degrees to 27 degrees. Now, when we did the same study in Indian context with extensive number of occupants, more than 9,000 occupants, we found a similar trend. However, what we found is that the occupants in India, that's why it's called India Model for Adaptive Thermal Comfort, is more adaptive than the occupants that were used in the ASHRAE model. And so you can see the maroon line, where you can see the temperature can go from 20 degrees to as high as 20 degree neutral indoor operative temperature. So this shows tremendous opportunity for us to use it in residences. And this is validated by various experiments, research, as well as by anecdotal evidences of the occupants who would say that we are actually freezing when the air conditioning is running. So this is one of the important tenet to start designing low energy cooling and ventilation strategies. Now, in the next slides, I'm going to talk about a process of how to go about designing ventilation strategies. And these strategies and the approaches have been developed under the research project that we have been working on. So here is another representation of the same chart that I showed in an earlier slide. So what you see in the x-axis is from January to December months, and the temperature, which one is on the y-axis. Whatever is in the dotted line shows the mean temperature of that 30-day period. So you can see how from January the temperature is going up to the mean temperature is going up to 35. Now when I say mean temperature of 35, that means there will be a variation throughout the day. So the diurnal variation may take the temperature to be 45 degrees. But the mean temperature or average temperature of the day is 30-35. And now you can see these different boxes in which you will see whatever is in blue, light blue color is the band where people are feeling most comfortable. So this temperature, which varies from 22 degrees to 27 degrees, is person feels very comfortable. And the band or the range of temperature that it shows 90% of the people, the band at which 90% of the people feel comfortable. Then if you expand it that little more, you will see a slightly darker blue band, which is where the temperature bands are slightly wider. So if you take a slightly larger band of temperature on cold side as well as hot side, then you will find a slightly loose band or area where 80% of the people in the space are expected to feel comfortable. So if you are trying to maintain 90% of the people comfortable, you need to have a slightly tighter band. But for 80%, you can actually, if you are willing to compromise on comfort, you can further allow it to your temperatures to float a little bit more. And beyond this band, the dark blue and on the top part is where people are feeling uncomfortable. So that's the temperature that you don't want to maintain in your space. So using this chart is first step, that what you do is a climate analysis of your building. So then you use that chart and you analyze the climate of your city. Let's say in here we are shown the climatic conditions of 9 major cities or 8 major cities in India. And you can determine that in what period of the year or how many number of hours in the year you have to operate certain strategies. So you can see if you are in Ahmedabad, about 2,900 hours of the year, and this is important especially from residents' point of view, 2,900 of the hours of the year you can operate your space in natural ventilation mode. So it shows that the climatic conditions are favorable, that 2,900 hours of the year, almost 1/3 of the year, is where you can operate your residences in natural ventilation mode. Now, whether you can effectively utilize it or not is something that depends on how you design your strategies. But the outside climate shows the potential to operate it almost 1/3 of the year. And it also shows when the period of the year when it needs to be humidified or cooled, or really need to be humidified as well as cooling. So as you can see, only natural ventilation is not sufficient for any of the climates shown in the 8 cities. But once you start combining low energy cooling systems and natural ventilation, you can try to develop an energy efficient and effective operational strategies for your building. So once you know how your climate is in a particular city, you need to start designing what ventilation and cooling strategies that you want in your residences. So in this slide, there are different strategies are shown. A strategy which shows is a concurrent mixed mode strategy. So it is a strategy where you are operating natural ventilation, so you are keeping the windows open while also operating air conditioning system. Now this strategy can only be used in a very specific scenario when outside is comfortable, more comfortable, but it's not sufficient to provide cooling, as well as having a more outside air leads to reduction of cooling load of your air conditioning system. So this is a specific scenario where you can run a concurrent mixed mode building. What you see in B is a very typical ventilation and cooling strategies that we see in our building, which is called a zoned mixed mode building. So in a zoned mixed mode building, one zone of your building is operating in natural ventilation mode, and the second zone of your building, for example, your bedrooms, may be operated in an air conditioning mode. It also depends on how much access do you have to outside air in your residences. Then there will be a hot day period where in all the mixed mode strategy, you will have to operate your space in a air conditioned mode. Or there will be a comfortable day when outside air is sufficiently cool so that you can provide comfortable environment by operating your natural ventilation openings. So this is strategy D, where you run it in natural ventilation mode. So in essence, you can run your building in either natural ventilation mode or AC mode. You can zone it in a different way, or you can run it in a concurrent mode in a very specific scenario. So once you decide what strategy is suitable for your specific building, then you start thinking about sizing your opening systems, right? That what should be my opening sizes to decide how do I size my natural ventilation system. So here we have shown we have actually used a typical 2-bedroom hall kitchen apartment, taken a master bedroom of that, and did an analysis of what ventilation rate would be needed for your apartment buildings. So if you are located in Ahmedabad, Delhi, or Mumbai, for example, your designed airflow rate would be 0.41, 0.34, or 0.54 meter cube per second. And how do you derive these numbers? You derive these numbers based on the chart that I've shown earlier, where 33% of the hours is when there is a climate potential to use natural ventilation. And then you use it to calculate how much air do you need to offset the heat load of your master bedroom. So whatever heat is generated in your master bedroom, what is the airflow that you need in your building? And if you put a 75th percentile, that means 3/4 of the hours when the climate potential is there, that's the band where you would say that if I can provide this much ventilation rate in my space, 75% of the hours when climate potential exists, I can utilize natural ventilation in your building. So that is how you can derive the flow rates required for your natural ventilation system size. Now, keep in mind that this is a one number. The reason why it's one number is that every hour it's going to be a dynamic process. You know, the amount of airflow will change based on this delta T inside and outside, as well as your air velocity outside or wind speed. But to design, you need to pick a number. So that's how you can select the opening sizes for your building. So that's why one threshold is required. For example, in air conditioning system, how we design, for the peak load, we design the capacity of the system, and then we design it accordingly. Similarly, for ventilation system, natural ventilation system sizing, we need to pick the airflow rate, which can provide 75th percentile of the hours when the natural ventilation is feasible, and we calculate the airflow rates. Once you know the airflow rates, then you use the design charts. This design charts are developed as part of the research project and is available in the a cooling guide that I will show in the end of the presentation, the link to that guide. So you can see you have to convert that airflow rate into an effective area of opening. So here is the chart that you use to convert what is the airflow rates that you need. For example, in Delhi, in Ahmedabad, and in Mumbai, and you map it with the effective area of opening that you need to design in your apartment, in your bedrooms. If you see when we studied a typical 2 BHK apartments, bedroom, hall, kitchen apartment, you can see that the business as usual opening area is usually not sufficient to provide the ideal ventilation rate for our residences. This is one of the reasons why we have to increase the operation hours of our systems, air conditioning systems or active systems. So once you know what's an opening area of the sizes, then you convert that opening area into actual window design. So once you know that this is my area 0.54 or 1.08 meters square, you then map it what the actual window and the effective area of the opening. Now this has a strong relation with the type of window you select. The sliding windows can only provide a half of the opening area. So you only can calculate opening area, even though the window area is 1.08, the effective opening area is only half, 0.54. So you have to then link it with either the type of door, balcony doors or casement or sash window you have, or you can design a purpose provided openings, PPOs, that will provide you natural ventilation and can have a damper in it to provide you additional area from which you can bring in the natural ventilation. So this is how one can use the design guide, what we call as a Le Cavalier design guide, to design the ventilation rates for your and the windows and the opening areas for your building, for apartment. Now, before talking a little bit more about low energy cooling systems, Deepa, may I request you to run the next poll?
Yes, sure. So let's launch the second poll, which is of course related to what you've been discussing so far. The question is on your screen. Can a mixed mode building operate efficiently in tropical climate? Yes, no, maybe. So send in your responses of what you genuinely think is the answer and not what you believe would be the answer. Yes, so 30 seconds are up. So we're receiving the responses very rapidly, in fact. We'll wait for some more time. Yeah, so 50 seconds. So we'll wait for 5 more seconds. Yeah, majority of you have already voted. So at this point, let's close the poll and let's share the results. Yeah, so 78% of you are saying yes, that mixed mode buildings can operate efficiently. And we still have, an 18% saying maybe and the rest saying no. So yes, some of us, like some of the attendees are still thinking that it probably may not be as efficient in tropical climate. So
Absolutely.
yeah.
I think that's a
Um,
very interesting note, but it's very positive to hear that 80%, and in comfort, we often talk about it's never possible to get 100% response. But it would be interesting in question and answer session to hear from maybe people to see when do they think that mixed mode building will work, or what are the challenges under which the mixed mode buildings will not work efficiently in tropical climates.
right.
Moving ahead with the next slides, let me talk a little bit about the low energy cooling strategies. Okay, so here it's important once you have designed your natural ventilation systems, your openings, it's important to then relate and say what kind of air conditioning systems should I use in my residences or in my buildings in general. So we have done some studies to compare different kinds of cooling technologies that are available in the market and analyzed what we call as an energy performance index, which is EPI, that presents a kilowatt hour energy consumption per meter square area of your building. And what you will see on the y-axis is the percentage comfortable hours. Now, ideally what we want is on the left top box, that you want really high comfort, but a very, very low energy consumption. What you see on the right side, which is a conventional cooling systems, where you will see a high comfort, but high energy consumption. Now, when you start looking at the low energy cooling systems, there are cooling systems that provide comfortable hours. When you think about a hybrid cooling systems, for example, radiant cooling systems or indirect evaporative coolers with a DX traditional systems, when you start hybrid systems, you reduce a little bit of energy, but you maintain comfort to the level of conventional system because you are relying on the backup side on the traditional systems. When you go really to the low comfort, low energy cooling systems, to further reduce the energy, you have to compromise on the comfortable hours inside your apartment. So this is where I think it's very important to take cognizance of the adaptive thermal comfort model that I've talked about. So if we look at in isolation, this is the scenario that we typically see. However, this scenario, when you start thinking about expanding your temperature band, further allowing it to modulate a little bit, then you actually open up avenues for this medium comfort low energy systems to actually operate efficiently with natural ventilation system. So that's when you need to start designing and incorporating your systems with the smart control algorithms. So once you incorporate smart control algorithms in your building, you can increase your comfortable hours and further reduce, allow your temperature band to float, and suddenly now you are going closer and closer to the ideal cooling systems with all the four strategies combined. Let me give you an example of what is the energy savings potential that exists with the use of adaptive comfort model. So when you do a different kind of system comparison, you will see that almost 15 to 30% energy saving potential exists when you allow your temperature band to float a little bit, allow it to modulate slightly warmer temperature inside your building. And this further reduces down when you start creating a hybrid system. So for example, a system here on the sixth system from the left, you will see there's a, you have a high efficient envelope with the direct and indirect cooler, so two-stage evaporative cooler with the our traditional DX systems. Suddenly you are seeing 40% reduction in energy consumption of your building. So this is where one needs to start designing low energy cooling systems while utilizing the hours. So you have to be smart about not only selecting the system, but also operating the system. One of the other important parameter to look at is air velocity. We often tend to forget that how air velocity can be very beneficial to maintain comfort at elevated temperatures. And this is especially true for tropically acclimatized occupant. So it's very important that how your velocity spatial distribution is in the space, and that's why it needs to be validated with a tool like computational fluid dynamics. So as part of this research project, we have been also looking at how the air velocity distribution is in the space and how it can be used effectively with this low energy cooling systems to maintain thermal comfort inside your spaces, inside residences. So once you again incorporate air velocity in this low energy cooling systems, you further expand the number of comfortable hours, you increase the comfortable hours and reduce the uncomfortable hours for your building. So with that, may I request you, Deepa, to run the next poll before I go on the control strategies for the residences.
Yes. Let's take the next poll. Yes, on your screen. Have you ever designed or operated low energy cooling system in tropical climate? Yeah, so maybe you are even, using a building or a space where such systems are also installed. Even that counts. So uh, take a pick, even if you've not operated on your own, but you've been a part of that space, then also you can, uh, select yes. Yes, the responses are coming in. In case if any of the attendees you would like to share your thoughts or your experiences of having actually operated such a system, you can just maybe raise your hand or put a question in the chat box, and we have the opportunity to have that discussion as well. Okay, so most of you have voted, so we'll close the poll now and share the results. So it's a 70-30 distribution. 70% has probably never designed or operated a low energy cooling system, and 30% at least have, yes, operated such a system. So that means we have a fairly sort of smaller percentage who have this experience of having, experienced either on the design side or the operation side, the low energy cooling system, and fairly very high percentage believe that these systems can operate efficiently. I mean, a mixed mode building, right?
Right.
So then that means if we probably know how we can apply this, if we are a designer, then we could have fairly good percentage of having this implemented in practice. Or if we are on, the operation side or the teaching side, then we have another role to play if we actually know how these things work.
Absolutely. I think this shows a great potential to apply the knowledge, especially an application of the low energy cooling systems in the design and operation of it. So it's showing a very good potential. However, it's hard to cover the detailed application, but at the end of the presentation, I'll talk about a design guide, like every design guide, which will provide the information to design in more detail how to go about applying, and hopefully that will encourage the participants to apply, design, and operate the low energy cooling systems. So the third part of my presentation, I'm focusing more on the control strategies of, so once you have sized your natural ventilation systems, once you have selected and designed your low energy cooling systems, the most important part is how do you operate them? Because if you operate it incorrectly, then it will not provide you the sufficient saving. So we have actually, through literature review, looked at 500 plus buildings, mixed mode buildings, one of my students did, to understand what is their operational strategies. And this is often reliant on the secondary data. So we did not go in the building to actually find out their operational protocols, but what the literature told us how they are operating case study buildings. And what we found is that 9 buildings out of 500 are using manual operations to switch between the natural ventilation and mixed mode. There are 5 switching control algorithms where they change, 2 of them change their operation between natural ventilation and air conditioning based on indoor and outdoor temperature. One has a schedule. So during the year, certain period of the year, they operated in natural ventilation and then automatically switched without accounting for what the outdoor condition at that point of time is. And 2 buildings had shown that they have a more detailed algorithms. They looked at humidity, wind velocity, and pressure differential to decide when to switch your buildings between the natural ventilation and mixed air conditioned mode. Only 7 buildings actually tried to open a certain degree of window opening or vent opening or HVAC systems. And more than 130 plus buildings did not have any specific rules of operation. So it was probably decided based on the occupants or the understanding of the facility managers. And this is another area where we felt that a tremendous amount of information is needed for somebody to actually complete the loop, complete the cycle, and achieve the energy savings in your residences. Then we looked at the research approaches that have been taken for the control algorithms, and we found researchers are looking at very fancy fuzzy logic controls, model predictive controls, stochastic distribution controls, certain mathematical controls. And we thought that there is, while all that is a very good from the research point of view, there is a really need for sophisticated physics-based control that are tested and validated, but when it's applied in the real world, it has to be easily replicable in the industry. So it can't be something which is very, very complex, because then in the real world it doesn't work. So this is where we started with in developing our ventilation and control strategies. We wanted to have a very, very simple strategies. So here is an example of a set of strategies that has been designed by us. So we divided the available system based on the space, what is available in the living room, master bedroom, and small bedroom. So once you reach at the control stage, you have to just modulate and operate the existing system. So what exists? Whether do you have windows in your space? Do you have dampers or ceiling fan, mechanical systems, dehumidifier, or ventilation? So based on these components, you can then decide how do you operate it to maintain comfortable environment while achieving energy efficiency. And you can see that certain spaces you are likely to not have all the components. So you can remove these components from the algorithm and still use the strategy in your building. And then based on the availability of components, we came up with a VCS is a simple word we use, or the acronym we use for ventilation and cooling strategies for specific scenarios. And these strategies and the flow chart of these strategies have been provided in the LeCAVE design guide. I'm not going to talk a lot about the flow chart or anything about the flow chart, but you can see that this integration of the natural ventilation with the systems, with the ceiling fan and the mechanical cooling system is a simple in concept, but a very, very difficult to implement if you don't have sufficient understanding of how can you make them integrated operation. But in principle, it's a very, very simple integration, and it is very intuitive for somebody to go and use it in their strategies. However, when we start doing that, we need to validate whether what we are saying in terms of the savings benefits exist in the real world or not. So there are two approaches we took to validate these control algorithms. First, we conducted a dynamic thermal simulations as well as CFD simulations to estimate that if we integrate these components, what would be the energy benefit and can we actually achieve the comfortable environment inside the space. And then second approach we took was to use the experimental facility that exists at CEPT University, which is a concept where we have a room within a room, where we model the different natural ventilation system in a simple room to assess what is the saving potential of these control strategies that we are proposing. And what we found through both is that we ran the simulation based on the experimented validated results. We took that results and then put it in a simulation model to show what would be the potential savings that exist without compromising the comfort. And this slide shows different percentages in terms of energy consumption for different ventilation and cooling strategies on the x-axis. So you can see as you go from VCS1 to VCS4, we are looking for more complex strategies, more savings from 15% to 55% savings in some scenarios, and also in different climates. So for example, in Bangalore, the savings even in the simplest strategy is quite effective. You can see 27% strategy benefit. We also added one more feature where we said whether sometimes there is a nighttime restriction of opening the window because of noise or safety issues. So if you have a certain restriction, what would be the energy savings in that context? Because nighttime is when there is a significant potential to use natural ventilation in your space because of the lower ambient temperature. So in essence, what I would like to summarize with these control algorithms, that even the simplest of strategies can provide you 15 to 30% savings. And if you go for more complex strategy, you can go as high as 50% savings, just due to control algorithms. After, of course, after selecting the correct natural ventilation system and low energy cooling system. So I know that my presentation covers a very high level information of all three components: natural ventilation system sizing, low energy cooling system sizing, and how to think about your control strategies. A lot more detailed information is provided in a design guide, low energy cooling and ventilation for Indian residences, which is available to download on our website. So feel free to go there and download and study more information of the design guide, or feel free to reach out to us if you have any questions. With that, Deepa, I hand it over back to you. Would you like to run the last poll before we start the question and answer session?
Yes, so last poll is, I think, very apt now to ask the attendees that do you now believe a well-designed control strategy, one second, is can improve the operational efficiency of a building? Yes or no? So send in your responses. So you've seen some of the simple strategies that actually can be used to size the openings, and even combining low energy cooling systems with natural ventilation. So with that combination, do you believe that a well-designed control strategy will improve the operational efficiency of a building? We'll wait for 10 more seconds and then we'll close the poll. This time we have like one unanimous answer. We don't have any mixed responses. So yeah, so let's close the poll. Most of you have voted. And you can see the answer. There's one answer. Yes. Everybody is saying it's 100% yes, that a well-designed control strategy will improve the operational efficiency. So Yash, it's pretty interesting if I just summarize, like initially the first poll where 64% of the attendees said that they are aware of low energy cooling systems but not sure how to apply it in building design, and 78% believe that the mixed mode ventilation systems do work, but only 30% had ever designed or operated such systems. But now 100% of them believe that well-designed control strategy can actually improve the operational efficiency of a building. So clearly, I think this guidelines, of course, it's elaborated further in the guide, will be extremely useful for everyone to actually pick up things that you can actually apply in your design, and maybe even assess the existing business as usual versus the potential that could be explored in a new building. So that's pretty interesting. Uh,
Yes, although there
yeah.
is a trick to this question, Deepa, it does not really say the operational efficiency of a mixed mode building. So
Hmm.
essentially what it means is that people think that control strategy is a very effective uh, uh, approach to improve the operational efficiency of any building. However, I think the verdict is still out for people whether they have bought a mixed mode building with natural ventilation sizing with the low energy cooling system. I think there is a verdict, it's still out. And we would be interested in knowing, if it stimulates all the audience to learn more about it and to apply it in their building, to start using it. I think then we would have done, as a research center, we would have done our job effectively as part of the research project.
Right, right. And in fact, some of the questions are on those lines. So let's jump into that and start taking the questions. I just want to share my screen a bit. Um, I think my screen
So
is
let
not
me,
visible.
I'll stop. Okay, I'll stop sharing. my screen then?
Yes.
Okay.
Can you see my screen?
Um,
I don't think so, right?
no.
Oh, okay. I have to first close the poll. Yeah, there you go.
Okay.
Yes, so we're back on.
Mm-hmm.
Yes, so let's start taking some questions now from the audience. So the first question here, I'll just read it out. Despite the efficiency by using natural ventilation in many cities, how to account for air quality also in the buildings, considering that the low air quality index in most of these cities?
And that's an excellent question. And this is a question that we often get when we talk about natural ventilation.
Yeah.
It's a fair understanding that it's very challenging when you are using natural ventilation to maintain the indoor air quality. There are several approaches to do that. Of course, just keep in mind that air quality is a dynamic parameter. It does not stay constant throughout the year. So there will be period of the year when air quality is moderate, which you can use for natural ventilation. When air quality is not good, of course you have to incorporate that in your control algorithms. You cannot just operate window when outside is extremely bad. You need to balance between the ventilation rates as well as maintaining the indoor air quality. But you can actually either design your space filtration strategy so that you can account for that additional particulate matter, for example, that you are getting in the space. So that's one way. If you know, you can design your space filtration system to account for that additional filtration. This again assumes certain threshold of outdoor air quality. If it's extremely bad outdoor air quality and you cannot directly use natural ventilation, then you need to consider using a filtration system through mechanical ventilation cooling, where you are still getting the outside air, but it's a filtered air with reasonable filters that can take care of the particulate matter. But yes, you need to be cognizant while designing natural ventilation of several factors such as noise, safety, and various other considerations like air quality before selecting your strategy for your building. And mechanical cooling system, mechanical ventilation with filtration is one of the good balance between the natural ventilation along with the low energy cooling system.
Right. Next question is what's the difference between a ceiling fan and a mechanical ventilation?
Ceiling fan is more considered as an air circulation device. So ceiling fan or pedestal fan, their prime purpose is to increase the indoor air quality circulation. So what we typically see in tropical residences. When we talk about mechanical ventilation, you are talking about bringing outside air through fan. When you say natural ventilation, you are using a natural means like windows, using the natural wind speed which is existing outside to get or the stack effect to get the outside air. So ventilation refers to the amount of outdoor air that you bring inside the space. So that's the difference between the ceiling fan, which just increases, does not bring an outside air inside the space, it just increases the air velocity or air circulation inside the space. But when you talk about ventilation, that means you're talking about bringing outside air inside the space.
Right. Next question. What is the role of infiltration in completely naturally ventilated building with fans? And how important it is in naturally ventilated buildings?
It's a very interesting question. So it's a difference between a controlled ventilation and uncontrolled ventilation. So when you talk about infiltration and exfiltration, that means whether the air is moving from outside to inside or inside to outside. You are talking about unknown quantity of air through unknown places. So you don't even have a sense of how much air will be moving in and out. With natural ventilation, still there is you have openings. You know from where and at what place the distribution of air will go to, although there is dependent on many external factors. So there is uncertainty in terms of how much natural ventilation you get, depending upon the temperature difference between inside, outside, and the air velocity. But it is more controlled than the infiltration exfiltration. So I would still recommend minimizing the infiltration exfiltration for all buildings, including natural ventilation building, so that you have better control of the air circulation. The importance of that is less compared to the completely sealed air conditioned building, where the infiltration leads to increased penalty in energy consumption. For natural ventilation, you are just going to have uneven distribution, uneven pressure differential to be able to clearly understand how your air path movement will be through natural ventilation. But to summarize, I would say in a continuum scale, infiltration is least controlled, and then natural ventilation, from where it is coming, but you don't know exactly how much air you are getting because of various external factors. And then you talk about mechanical ventilation, because the fan flow, exactly how much ventilation you are getting. So depending upon your application, you need to select one. But in all scenarios, like I said, we should try to minimize infiltration. However, the penalty of infiltration is minimal for natural ventilation, except that you may not get sufficient quantity of air if the pressure differential already exists.
We'll take a couple more questions. There's so many coming in. The next question is, will the mixed mode system be affected by different building envelope? For example, high thermal mass of a wall and light walls.
Absolutely. So let me answer it two ways. The impact of mixed mode building systems will have an influence of the good envelope systems. So in other words, if you have low heat gains, if you have good envelope, then you need less quantity of outdoor air to remove that heat gain. The delta T required for tighter envelope through natural ventilation is lesser than what you are getting it for the leaky envelope, or through when you don't have a energy efficient envelope. You will need more quantity of air and more temperature differential between indoor and outdoor to remove that heat gain. So more having an efficient envelope increases the effectiveness of your mixed mode ventilation systems, or mixed mode building performance improves with a better envelope system.
Right. Another last question we would take. Then there are some more. Maybe Yash, I can send it over to you,
Sure.
which you could then respond to. The next question is: the ASHRAE Adaptive Comfort Standard has been designed for free-running buildings, but IMAC considers air-conditioned buildings as well. The users should have the controllability to adjust their temperature, of course, but shouldn't the building design be based upon the PMV method, that is the 20 to 25 degree range, instead, so that the building still remains efficient if occupants opt for lower temperatures?
So
It's a
there are
fairly
multiple,
long.
yeah, it's a long, but it's a multi-layered question, I would say. So ASHRAE 55 is using natural ventilation. The adaptive model is only proposed for natural ventilation, so that's true. However, recent studies have all shown that the mixed mode buildings, which is where you do, natural ventilation and air conditioning combined in a, you change the operation mode, would also be able to use adaptive comfort mode. So sufficient evidence exists that you do not always have to rely on PMV method to size the mixed mode buildings. If you are talking about a completely air conditioned buildings, then PMV method is fairly have been fairly proven and established. Even the adaptive studies have shown that the people who have always stayed in air conditioned mode lose the chance of or lose the adaptability over time, and they cannot adapt with the change in temperature. They would prefer a more controlled environment. So if you are using air conditioned building, then definitely it's PMV model is fairly acceptable way to size your system. But I would say if you are using a mixed mode buildings, you have opportunity to operate your system based on a higher temperature. About the sizing systems, I think that still you can size it for 22, but you are going to over design your capacity. If you can size it slightly differently, considering what would be the operative temperature based on the adaptive model at certain peak period of the year, and actually design it and operate it. And that gives you opportunity, like I shared in my presentation, to not limit to only one or two types of traditional system, but you can start using alternate cooling methods and technologies to in your design. So I think it's very important to not stay restricted to only PMV model for mixed mode buildings, which is what typically I've been talking about in the presentation. And I missed the last, I forgot the last question part of it. Yeah, I mean, this occupant control has been found to be very effective. There is no doubt that more occupant control you give to the occupants, they have been found to be more accommodating at higher temperatures. So if somebody has their own personal fan, the studies have shown that they will be accepting the slightly higher ambient because they know that whenever they feel warmer, they can turn on the fan. So it's always beneficial to provide the occupant control of their environment. Studies have found that to be true, what the questioner asked. Did I miss any part of that question?
No, only in terms of control, the question said that if given a choice, the occupants would opt for lower temperatures. So
I actually, the studies have shown that people do not want lower temperatures. I mean, so when we do a thermal comfort survey, we asked what's the current temperature, and we measure what's the current temperature. We asked what is your comfort level, and then the next question is that do you want it to be slightly cooler or slightly warmer? And then the data, the evidences show that people actually who are acclimatized for in certain climate would actually do not want to maintain a very low temperature. They actually feel uncomfortable at that temperature. Now, I am generalizing a lot just to simplify the message that I'm in the presentation. But the point is, you can, as a designer, think about having a backup or you can over design the system just in case the load increases. There are many factors that play in designing the air conditioning systems and the sizes of that. But I think there is a fair bit of data now exists to be able to use it for alternate cooling system and not design it for 22 degrees and not go for the worst case scenario.
Right. Yes. So I think we'll take one last question and then we will wrap up the session because we have 5 minutes up time. Which software have you used for the climate data analysis that you showed in your presentation? That's our last question.
So actually, we haven't used any software. So there are many software that exist where you can do a climate analysis, but we have done, a fundamental calculation of what the outdoor conditions are and just the heat balance equations to come up with the climate analysis. Uh, and it's as simple as knowing what the temperature is, what the heat load is, and when do we consider certain operation strategies. But you can, there are tools available on our website which does a climate analysis for you, and there are online free tools also available, such as climate consultant, that you can do to quickly analyze the climate data.
Right. Thank you so much, Yash. So, just before we conclude the session, a few announcements to make. Firstly, some of you did send in a message that you've logged in a little bit late and you missed the beginning of the session. So we'd like to inform you that we have a YouTube channel, NZIP India, and all the webinar recordings of even the past sessions are available there. So you may go there and access to the recording of this session as well in a couple of days. For the next session, the next webinar that we have is on 11th November in the morning at 10:30 a.m. A climate-based approach to carbon neutral design. Very interesting topic again, and the expert speaker, Dr. Pablo Laroche, will share both insights from practice as well as teaching. So do sign up for that as well. The information for this is available on our website, nzeb.in, and you can register for the webinar. And that's about it. So if you have any questions or you would like to get in touch with the NZEB team, you can write to us at nzeb@edsglobal.com. We hope you enjoyed today's session and look forward to the next one. Thank you so much, Yash, and thank you to all our attendees. See
Thank you,
you in the
Deepa.
next session. Yeah.